right, so today, the last time we met, I introduced material on chapter 16 that will be covered in exam 8 on acids, bases, and pH. And since we finished the introduction on that day, today I'm going to start the review. And most likely I can get through the review today, which means, and it's on your syllabus, it's listed as a buffer day. So the next time we meet, which this is Thursday, it'll be next Tuesday. The next time we meet, I will open up the Zoom session for any problems that you may have. And I'll stay open for probably a half hour, just to see if anybody Zooms in and needs special help. Okay, so let's get rolling with the review. I've taken the review document that is available in Brightspace, and if you were here in person, you get a hard copy. And I've highlighted several of the problems that I want to be sure and cover. So it's not that the rest of them aren't important. It's just that these are unique. Usually, they cover unique concepts. All right. So let's start with number 3. All right. Which of the following is the strongest conjugate acid? Strongest conjugate acid. Remember, conjugate acid-base pair, you have something like this, and then that would be the conjugate base. So when we say conjugate acid, it could be this one, or it could be a base going to an acid over here. Like, for instance, that would be the base. Conjugate acid would be that, because the base accepted a proton. Now this ammonium ion has a proton available to donate. That makes it an acid. Let's see what our choices are. All right. I am detecting from the nature of this question that the creator of the question is looking for this side of the equation. This is the conjugate side. This is the non-conjugate side. This is the reactant side. So the conjugate acid would have to be able to donate a proton, but it would have to be derived from a base. HOCl, hypochlorous acid, HCN, hydrocyanic acid, HF, hydrofluoric acid. Those are all acid reactants, right? Their conjugate base would be OCl minus, CN minus, and F minus, and they would not produce a conjugate acid. The only one that is a conjugate acid is ammonium ion. Hold on a second. Okay, I was reading more into this problem than I should have. If we're looking for the strongest conjugate acid, okay, all right. What you want for the strongest conjugate acid is the weakest base, right? So the question here becomes, the strongest conjugate acid requires the weakest base. So we would be looking at this one, this one, this one, and this one. Right? Those would be the bases that would produce a conjugate acid. Now, how would they do that? Well, each one would have to react with water. Right? And then this would produce a conjugate acid plus hydroxyl. This would produce that conjugate acid plus hydroxyl. This would produce HF plus OH minus. And this one would produce NH4 plus OH minus. Okay, now half the battle in solving problems like this is to understand what the problem is asking for. And sometimes you have to go to what are the possible answers that are given to make sense of the question. And that's the dilemma we're in now. So we're looking for the strongest conjugate acid. Which one of these is strongest? Which one is most likely to donate a hydrogen? We can look at it two different ways. If we know something about the strength of these, we can say something about these, right? If we want the strongest acid, we need the weakest base. Okay? Which one of these is the weakest base? Well, the weakest base is the one that is least likely to accept a proton. Strongest acid is the one that is least likely to give up a proton. So what we need to do is look at the, we can approach this from two ways. We can look at its electronegativity. How strongly do each of these groups attract a proton? Ammonia is fairly weak. Cyanide is extremely weak. And hypochlorite ion is extremely weak. This one has the highest electronegativity, which should make it the strongest acid. All right, so that's my logic to answer this question. All right, number 4. Calculate the hydrogen ion concentration in a solution that has a pH of 8.82. If it's a pH of 8.82, what is that equal to? That's equal to the negative log of the hydrogen ion concentration. Right? And remember the nature of logarithms. How do logarithms work? The base to this power is that number. But we can't have a negative over here. The negative has to move on this side. 8.82 equals log hydrogen ion concentration. So now if we take this value, 10, to that power, 8.82, that will equal the hydrogen ion concentration. So all we need is 8.82, change the sign, and then raise 10 to that power. And remember, the decimal points here, the number of decimal points here tells you how many significant figures are in the non-transformed value. So that means I have to round it off to 1.5 times 10 to the minus 9 molar. Okay. Right. Let's go to number 5. A solution is prepared by dissolving 111.9 grams of hydrogen chloride gas okay, in enough water to make 160 liters of solution. So the total volume, this is the mass, total volume equals 160.0 liters. We want to know what the pH is. Well, when you dissolve this in water, it will completely dissociate. It will do in solution, it will make the same molarity of hydrogen ions. That's what we need to know to find the pH, concentration of hydrogen ions. So we need to find the concentration here in terms of molarity. That is mass. You've got to convert mass to moles before you can calculate the concentration. So molarity is going to be moles per unit volume, and the volume has to be in liters, so that's good. It's already done. This one, though, grams of HCl, we need to convert to moles, right? Numerator, denominator cancels, but we need a value there. What's the mass of 1 mole of HCl? Well, hydrogen is 1.01, chlorine is 35.45 grams per mole. So that would be 36.55. We just divide that into 111.9. 36. 5. And we got 4 significant figures. 3.062 moles. Okay, now we can calculate the concentration. And once we calculate the concentration of this, we also know the concentration of that, because this completely dissociates into that. All right, so we got 3.062 moles per 160.0 liters. And I get 4 significant figures, 1.913 times 10 to the minus 2 molar. And that is not just HCl, that is hydrogen ions. Now we can do the pH calculation. Negative log of 1.913. I can do better than that. Times 10 to the minus 2 molar. Okay, so I've already got it in my calculator. I'm just going to take the log of it, change the sign. And the number of significant figures here is the number of decimal places in our answer. So we can have 1.718 pH. All right, the problem rounded it off to 3 significant figures, which it should not have done, but be that as it may, D would be the best answer. I mean, if you got something in here like, if you truly got the right answer and it was say 1.6, then it would be none of these. But 1.718 can be rounded off to 1.72, so that's your best answer. Right. Number 6. A solution has hydroxide ion concentration at 5 times 10 to the minus 4. What's the pH? All right. Hydroxide ion concentration, we know, is this value times 10 to the minus 4 molar. Okay. There are 2 approaches to this problem. You can either use pKw equals 1 times 10 to the minus 14, which equals the concentration of hydrogen ions times the concentration of hydroxyl ions. Solve for hydrogen ions and then create pH. Or we can take this one and say POH equals negative log of 5 times 10 to the minus 4. Then once we get that value, subtract it from 14. I like this way better. So let's say 5, 4, okay, take the log of that, change the sign. So I have two significant figures. I have 3.30. POH equals 3.30. pH then is equal to 14 minus 3.30 equals, let's see, two decimal places. 10.70 pH. Okay. You can do it either way. I just did it the way I prefer. All right, number 7. As water is heated, its hydrogen ion concentration increases. All right, this is pure water because it doesn't tell you that there's anything else in there. It's just water. So when we increase the temperature, we also increase the hydrogen ion concentration. All right. So what does that mean for the reaction? Right? Water can do this thing. Right? It's going to equilibrium. It's going to produce like that. Okay? Or we can write it this way. This is the correct chemical reaction. This is what it does. This is for convenience, to simplify. And to answer the question, this one probably works better. So if we look at what happens when you increase the temperature, you're forcing the reaction to produce more hydrogen. It's like that. The equilibrium is shifted to the right. Okay. Where did this hydrogen come from? It came from that water. Where did this hydroxyl come from? It came from that same molecule. So for every one of these that you produce, you get one of those. That means even if you increase the temperature and you get more of these, you're also going to get more of those in the same proportion. So they're always equal. If it's just water, they're always equal. That means the water is still neutral and the hydrogen ion concentration is equal to the hydroxyl ion concentration. So if the hydrogen ion concentration increases, the hydroxyl concentration increases also. That means not just A, but D is also true. Okay, that's why E is the answer. A and D are both true. Now, if you increase the temperature, what happens to pKw or Kw? They will change. Those values will change. If you increase the hydrogen ion concentration and the hydroxyl ion concentration, multiply them together, you should get a larger value for Kw. and a smaller value for pKw. Excuse me. Number 8. All right. Identify the Bronsted acids and bases in the following equation. All right. So let's put what's given to us. HSO3 minus, correct? Yes. CN minus. And that yields HCN plus SO3 2 minus. Okay. Which is the reactant acid? It's the one that donates a proton. So how do you know which one donated a proton? Well, you look at this part. That's got a proton. Well, that doesn't have a proton. So this is the most likely candidate. And if you look at the other side, you find that's all that's left. So that proton was donated there. That makes this the acid, this the base. And now on this side, we have the conjugate acid and the conjugate base. So in terms of our answer, it's A, B, A, B. Okay. That was easy enough. Number 9 coming up. Which of the following is a conjugate acid-base pair? All right. Remember the conditions for a conjugate acid-base pair. First of all, the core of the molecule, not including the hydrogens that can ionize, that must be the same on both sides. We're saying here that and that acid base. In addition, not only are these two parts the same, you can only lose one hydrogen at a time. Right? So if we say, for the first one, HPO4 2 minus, HPO4 2 minus, and they're telling us PO4 3 minus is the conjugate base. Is that true? Well, this part's the same, and it's only lost one hydrogen. That's a conjugate acid-base pair. Right? We found our answer. It's A. And the reason I know that is because this is multiple choice, and B, C, D, and E are all unique answers. If it asks for the conjugate acid-base pair and we found it, we can stop there and move on. 10 is a little more involved. Number 10. Because in this case, the question is, which one is not a conjugate acid-base pair? That means we have to look at each one until we find the one that's wrong. Okay. So let's see what we got. HCN and CN minus, correct? Yep, that's good. One proton missing, that part's the same. That's a good. That's an acid-base pair. How about CH3, NH3 plus? CH3, NH3 plus. And what is CH3, NH2? CH3, NH2. Yeah, it's missing one proton from here to here. And the rest of the molecule is the same on both sides. Now, the trick to this one is to recognize that these hydrogens are not ionizable. There's one here that can ionize. That's why it's missing over here. So this is a conjugate acid-base pair. That's true. How about HCO2H? HCO2H. And HCOH. H. All right. We've got the same hydrogens on both sides. What's missing is an oxygen, right? Right? That cannot be an acid-base pair. How about the next one? Well, we found one that was wrong, right? So we found our answer. But if we go to the rest of them, that's lost a proton. Rest of the molecule's the same. That's a good one. And E should also be a good one. HClO2 and ClO2 minus. Yep. Lost that one hydrogen. That part of the molecule is the same. That's good. So C is the answer. That's the one that is not a conjugate acid-base pair. Eleven. This one might be redundant. We've done one like this before. Calculate the hydrogen ion concentration in solution that has a pH of 9.16. Okay, so we've done one like this before. 9.16 equals the negative log of the hydrogen ion concentration. Right? So hydrogen ion concentration should be, that was the question. Yeah, hydrogen ion concentration should be 10 to the minus 9.16. Okay. So if I did my calculations correctly, it should be 6.9 times 10 to the minus 10 molar. Okay. All right. Some of these problems are similar solutions at their core, but they're presented differently. So the key is to recognize the question for what it is. 15 is calculate the pH of an acid solution containing 0.044 molar HNO3. Okay, what's going to happen to NO3 in aqueous solution? It's going to completely dissociate. This is a strong acid. Right? So this is 0.044 molar, and it's going to produce 0.044 molar hydrogen ions. So now that we know that, the calculation is simple. Okay. If I calculate correctly, I should get a pH of 1.36. Okay. That was simple enough. What's the pH of 4.9 molar solution? Okay, I'm going to go ahead and just put this one down here. So if we have HClO4, which is what? That is perchloric acid. It is very strong. Right. And then produces the perchlorate. Right. So if we know that the concentration is 4.9 molar here, then it's definitely 4.9 molar there. And we can calculate the pH just like any other. This is a mathematical transformation. There's nothing special about it. Negative log of that value. I want to do that one by hand. 4.9. Take the log and change the sign. Okay, this is negative 0.69 pH. Okay. So you can get negative pH values. It's just that they don't mean that much. when you get a strong acid at that concentration, this concentration right here, this number is more important. It's more, gives you more information than that one does. It's only when you have small concentrations that you get a better idea of the behavior of the solution with the pH. But the high molar concentrations like this that would give you a negative pH are more informative as the molarity. All right. Another one. Let's see. Nitric acid. What's the pH of 0.25 molar? Well, that's a strong acid. Right? So it's a simple calculation. And I get 0.2 significant figures. 6, 0, 0.60. Yeah, 0.60 pH. All right. About 18. A solution has a pH of 3.16. pOH of this solution is what? Right. This is really simple because pKw equals 14, which is also equal to pH 3.16 plus pOH. So all we have to do is subtract 3.16 from that value. Oops, my mistake. 10.84 pH. Okay. Let's see. Scroll. Here we go. Let me see there. Some of mine is cut off on that edge. Okay, I think we can see all of it now. Which of the following is true for a buffered solution? Remember what a buffered solution is. Buffered solution, in terms of pH, is that once the solution is created and it's identified as a buffer, if you add strong acid to it, it will resist a decrease in pH. Or if you add a strong base to it, it will resist an increase in pH. Right? So A says the solution will not change its pH very much, even if a strong base is added. That is true. A is true. How about B? The solution resists any change in its hydrogen ion concentration. Yep, that's another way of saying it. Okay, how about C? Any hydrogen ions added will react with a conjugate base of a weak acid already in solution. That is absolutely true. If you have a weak acid in equilibrium with its conjugate base, then if you add hydrogen ions here, it will force the ship this direction. If this is weak as an acid, this is strong as a base. And what we mean by a strong base is the base is looking for protons and it will get them wherever it can. If you add hydrogen ions, they'll definitely react with that strong base. Okay, so this one is also true. Let's see, we have a D for a selection. Let's see what D says. The solution will not change its pH very much, even if a concentrated acid. Well, that's also true. Right. So I guess E is all of the above. Yep. That one's also true. All of the above are true about buffered solutions. All right, next. 24. A solution has OH minus or hydroxyl ion concentration of 3 times 10 to the minus 7 molar. The hydrogen ion concentration in solution is what? Okay, this is one where it's probably more efficient not to calculate pH or POH. In this case, we would say PKW equals KW, pardon me. KW equals hydrogen ion concentration times hydroxyl ion concentration. So that means 1 times 10 to the minus 14 equals, and we're given the hydroxide ion concentration. So this is our unknown, that one. And we have a value of 3 times 10 to the minus 7 molar. Right? So now this concentration is simply the KW divided by the hydroxide concentration. And I get 3.2 significant figures. There you go, 3.3 times 10 to the minus 8 molar. Okay. Next. All right. Here we go. A weak acid. Weak acid, HOCl, hypochlorous acid, is in solution with dissolved sodium hypochlorite. Okay. It's in solution with dissolved sodium hypochlorite. So what does sodium hypochlorite do? Well, remember from our solubility discussions, and you can look it up on the solubility chart, all alkali metal salts are soluble. So sodium hypochlorite is going into solution with separate sodium ions, separate hypochlorite ions. So what it will produce is this and this. Okay, and this is in solution. All right, and they're in that same solution together, all those components. If HCl is added, which ion will react with the extra hydrogen ions from HCl to keep the pH from changing? Well, recognize that this is a spectator. Sodium is not going to react with the hydrogen ions anyway because it's a cation too. So the reaction itself is like this. I'll tell you what. Let's write it out with the true chemical behavior. All right. So this is going to transfer here. This is going to go like this. This is what actually happens in solution. And we're going to produce hydronium ions plus OCl minus. Okay. Now, the way we created this solution was to add some of that and some of this. And this is what happens in solution after we create it. Right? We come to equilibrium. This will react with some water, maybe, and produce hydronium ions and hypochlorite ions. Once it reaches equilibrium, then we can say, we can answer the question. hydrogen ions. So where are they going to be? They're going to be right here. Hydrogen ions. Right? Well, what are the hydrogen ions going to react with? They're going to transfer this proton over here to the OCl minus. That's why D is the answer. This is the strong acid. This is the weak, strong acid. Weak acid, excuse me. That's a weak acid. Weak acid, strong conjugate base. So the hydrogen ions are going to react with a strong conjugate base, which is hypochlorite ion. That's why D is the answer. Scooch that a little bit. There we go. 28. Which statement is true for a strong base solution with a concentration greater than 1 molar? Okay, strong base with a concentration of 1 molar. Actually, it doesn't have to be hydroxyls. Yeah. It could be anything else that is a strong base. So what happens with that strong base? Once it's in solution, it's going to take hydrogen ions from someplace. But if there's only, if we say the base is 1 molar, all right, to answer this question, actually, we need to assume that the strong base is hydroxyl. Otherwise, it becomes more difficult, becomes more complicated when we try to address strong base like hypochlorite ion, something like that. So if we assume that, then if it's 1 molar in this concentration, 1 times 10 to the minus 14 equals hydrogen ion concentrations times hydroxyl ion concentration. Right? And that's always in solution. So if this is 1 molar, what does this have to be? 10 to the minus 15. See, I can do better than that. Minus 15. Because this is 10 to the 1, right? And those both together have to be 10 to the minus 14. So that means the hydrogen ion concentration is extremely low. Now, pH is greater than POH. Concentration. Which statement is true for a strong base solution with a concentration greater than 1 molar? pH is greater than POH. Okay. So if we do the P transformation, then what's the POH? The POH is the negative log of 1, right? And 10 to what power is 1? Anything to the 0 power is 1. So this would be 0, right? POH is 0. How about pH? 10 to the minus 15, negative log of that. So it would be pH 15 equals pH. So the pH is much, much larger than the POH. So A is true. And of course, B can't be true. How about the pH is less than 14? No, it's greater than 14. pH less than 0? No. Okay, so the only one that fits the bill and doesn't allow us to say 2 of them are true is A. pH is greater than POH. That question would be much better if we said for not just a strong base. If we said a strong Arrhenius base that has a hydroxyl in it, that would be better. A strong Arrhenius base at 1 molar will produce 1 molar hydroxyl? That would be a much better question. A solution with a pH of 2. Oh, just says 2, sorry. With a pH of 2 is how many times more acidic than a solution that's pH 6? We're comparing these two solutions, right? So when we say how many times more acidic, is this one more acidic than that one? Yeah. The lower the pH number, the more acidic. But we want to know quantitatively how much more acidic. Well, this is a logarithmic transformation, right? So between these two, you have 2, go 3, 4, 5, 6. 1, 2, 3, 4. We have 4 steps. And what do those steps mean? Those steps are powers of 10. Because our log is base 10. Okay? So 10 to the 4, we're taking 4 steps. 10 to the 4th is equal to 10,000 times more acidic than pH 6. That's why D is the answer. Okay. Let's see, who's next? 32. A buffered solution contains HNO2, right? If it has HNO2 in aqueous solution, and we're saying this is a buffered solution, that means that this must be a weak acid. And it produces in solution NO2 minus. But when we produce a buffered solution, you need some of this and some of that at the beginning. And actually, the best balance between the two is a 1-to-1 ratio. The same molar, this is molar ratio. So you have the same concentration of this as you do that. That is the ideal buffer for any of these weak acids. Okay, so what else has to be in solution? It also contains that anion. But how do you get that in solution? You can't take it from here. So if you're going to put them together initially, you have to put this one in there as a salt, right? It needs a cation. And the best cations are the alkali metals, either sodium or potassium would be a good one. Let's see, we could use rubidium, but that's a little overkill. Lithium even. Right. Any one of those has the salt of the nitrite ion. And this molar concentration is equal to that molar concentration. That would be an ideal situation. So out of all those that we had to choose from, A would be the best one, right? Potassium nitrite in solution with nitrous acid will produce the proper buffered solution. All right, 33. Consider the reaction. Okay, that looks like acetic acid to me. Which species is the conjugate acid? Okay. If we have C2H3O2, yes. C2H3O2 is acetic acid, and it actually does react with water and produces the hydronium ion. plus the acetate ion. Okay, so what do we have? Here's the acid. That makes this the base. Now this is the conjugate base of the acid. And this is the conjugate acid of the base. Okay, so it's asking for the conjugate acid. That would be B. That's the conjugate acid right there. When you put this in solution, there's nothing else in there but water. Water's the only thing it can react with. So it, that's all I can say about that. That's true. Which of the following is not a conjugate acid-base pair? Right? 35, yes. All right, we have several choices. A, B, C, D, and probably E, right? Yeah, they're all unique choices. So we need to find the one that's not a conjugate acid-base pair. Right, the first one has sulfuric acid, and then its conjugate base, it says, is that one. What's wrong with this picture? Well, this part is the same on both sides, but you have to lose 2 protons to get to the base, right? Can't be. We found our answer. If you look at all the others, you'll have the same core of the molecule on both sides, plus only 1 proton missing from the acid to the base. And that's true for all the rest of them. So A is the wrong one. It's a bad one. All right. How about this one? 37. So given the following list of Ka values, which of the conjugate bases is the strongest? Okay, if we have Ka values and we're looking for the strongest conjugate base, then in order to determine the strongest conjugate base from the Ka value, we need to find the weakest acid. So based on the Ka, we want the weakest acid. What are our choices? Well, the conjugate bases are over here. And E is all. E is all. That doesn't make any sense, but I put it anyway. Right, so there's a base. There's a base. OCl minus and Cn minus. All right. Which one is the strongest base? Look at the Ka values. How about the Ka for HCN? Or HOCl, or NH4, or HF. Okay, compare those. Which one of these is the weakest acid? Look at the values. Look at the powers of 10 first. Which one has the largest power of 10? Minus 10, minus 10, minus 8, minus 4. Minus 4 is the strongest acid in that group. So it will be the weakest base. All right, let's go for the smallest value, which will give us the weakest acid. Well, the first two are 10 to the minus 10. So since the powers of 10 are the same, we go to the coefficients. And which one is smaller? The ammonium Ka is 5.6 versus hydrocyanic acid, which is 6.2. So the smallest value there is 5.6 times 10 to the minus 10. So this one is the weakest. That means this one should be the strongest base. Strongest conjugate base. Okay? Number 40. Solid calcium hydroxide is dissolved in water until the pH of the solution is 10.39. The hydroxide ion concentration of the solution is, okay? To answer this question, it doesn't matter that calcium hydroxide was used, right? Once we know the pH, from then on, it's purely a hydrogen ion, hydroxyl ion calculation. All right, so if the pH of the solution is 10.39, right? Yeah. If the pH is 10.39, that means the pOH is equal to 14 minus 10.39. Right? So let's see, that'd be 1. This would be 6. And this would be, oops, I'm mistaken. This would be 3, right? That would be pOH would be 3.61 pOH. Okay. Oh, wait a minute. Oh, hydrogen ion concentration. I'm not finished yet. This is pOH, which is equal to the negative log of the hydroxide ion concentration. Okay, so what we need is 10 to the minus 3.61 equals hydroxide ion concentration. So let's say 3.61, change that sign in power of 10, and that's 2.2 decimal places, 2.5 times 10 to the minus 4 molar. There you go. Now we got the right answer. All right, 41. Choose the pair of concentrations that cannot be in a given aqueous solution at 25 degrees C. All right, so look at the answers. We'll give you a clue as to how to approach the problem. Hydrogen ion concentration, hydroxyl ion concentration. In aqueous solution, remember, this product at 25 degrees is always like that. Okay? So if we say A, B, C, D, and E is all of these can exist. Okay. So all is possible. So what do we have here for these two concentrations? We have 10 to the minus 13, and hydroxyl is 1, which is 10 to the 0, correct? Yeah, 10 to the 0. So 10 to the 0 times 10 to the minus 13 is what? Is 10 to the minus 13. Right? That's not it. How about B? 10 molar, right? 10 molar, and hydroxide is 10 to the minus 15. So this is 10 to the first power. Right? 10 to the first power is 10. So this would be 10 to the minus 14. Yep. That one works. We're looking for the one that cannot be. All right. So far we found A cannot be. E says all of these can exist. Okay, we found our answer then, right? A cannot exist. If we do the rest of them, 10 to the minus 3 and 10 to the minus 11 equals 10 to the minus 14, right? And then the last one is a neutral solution. 10 to the minus 14. Okay, so we found our answer. A is the one that cannot exist. Let's see, 42. What's the pH of a solution prepared by dissolving 96.1 grams of sodium hydroxide in enough water to make 3.2 liters? Okay, so we got a mass of 96.1 grams of sodium hydroxide, which is a strong base. So everything we put in solution ionizes. Well, actually, it dissociates. What I mean by dissociates means even in this compound, it has positive sodiums and OH negatives. So all it has to do is break apart. Okay, so we need how many moles? Grams here, moles there. So what's the molar mass of sodium hydroxide? Well, sodium is 23. Oxygen is 16, and hydrogen is 1.01. Let's see, is 10, 40.01 grams per mole. So 40.01 divided into 96.1. Is, let's see, 2.40 moles. Okay, that's how many moles of sodium hydroxide we add. Now we're going to put that in a solution that the final volume of the solution is 3.2 liters. So the molarity equals 2.4 moles divided by 3.2 liters. Okay. Which is 0.75 molar. And this is the molarity of the sodium hydroxide, but for each mole of sodium hydroxide, you get a mole of hydroxide. So this is also the concentration of hydroxides. The question is, what's the pH? So let's do the pOH. pOH equals negative log of 0.75. Okay. Which is, let's see, 2 decimal places. 0.12 pOH. And pH is equal to 14 minus 0.12. Which should be, let's see, 13.88, right? Let's see, add those together, yeah, 13.88 should be the pH of this solution. All right, who's next? Oh, we're done. Well, those are all the ones that I had selected for review out of that document. When you look at the other problems, if you have questions about them, then come back on next Tuesday. And I will zoom in for half hour or so, just to be sure if anybody comes in and needs needs some tutoring. You can also come to my office. I'll probably Zoom from my office rather than set up in here in this classroom. I'll Zoom from my office and I'll put a note on the door in case somebody shows up in person, then they'll know where to go and find me. But I'll be Zooming for about a half hour just to be sure that if there's anybody who needs extra help. Otherwise, the review for this exam, number 8, is done.